All right, so next one is the AstraZeneca Oxford vaccine. This one is not mRNA technology. This actually uses something really interesting. It doesn't use a lipid nanoparticle. So you see this brown structure here. This brown structure, which is housing the nucleic acid inside of it, is called a chimpanzee adenovirus. And this chimpanzee adenovirus, chimpanzees haven't really been exposed to a lot of the human kind of population, so we won't generate an immune response to the adenovirus itself. We're going to try to generate an immune response to the protein that's going to be expressed by the DNA housed in it, and that's why we're using the chimp adenovirus. But inside of the chimpanzee adenovirus is a DNA molecule. Okay, there's a DNA molecule, and the same kind of process is kind of working here, where this DNA expresses a protein that is very similar to the S peptide of the virus. So the same kind of process is what we're kind of doing here, is we're kind of taking into consideration that what's our goal? We want to generate an immune response to this S peptide, right? And so ways that we could be doing that is by kind of converting this right into an mRNA, and then basically converting this into DNA, and then incorporating that DNA into this chimpanzee adenovirus, right? And then whatever this DNA is expressing inside of this host cell, it'll lead to antibodies directed against the S peptide. So how does it do that? It's pretty much the same kind of process here. The chimpanzee adenovirus, when you inject it in, right, deltoid, it'll then, again, latch on to this host cell. When it latches onto the host cell, it'll release the DNA into the host cell, right, into the cytoplasm. And then when it releases that host DNA into the cytoplasm, what happens is the DNA migrates into the nucleus, right? So you have your nucleus of the cell. Once in that nucleus, it does not get incorporated into the DNA, from what AstraZeneca says. They say that they use the host cell's enzymes to convert the DNA into mRNA. Then they take the mRNA that's generated here and put it out into the cytoplasm, where it will then interact with the host cell's ribosomes. Then the ribosomes, whether free or bound to rough endoplasmic reticulum, will then get translated and make proteins, right? And these proteins will then do what? They'll get expressed onto the cell membrane. And you guys already know what happens here. What happens? It expresses this on MHC1 complexes and MHC2 complexes. And then the result is the same, right? We're not going to go through the whole process because we already talked about it, but you have your T cells here, your helper T cells. They generate an immune response. And that does what? It tells B cells to turn into plasma cells. And then these plasma cells generate antibodies. And these antibodies are generated against the S peptide on the SARS-CoV-2 virus. Right? And you're generating memory T cells as well. So a lot of that stuff is still happening. The other thing is you still have those cytotoxic T cells. And those cytotoxic T cells are still going to be interacting with the MHC1 complexes. And again, when they're doing that, they're still going to be releasing destructive molecules that cause the damage of this host cell. But also release cytokines that are going to aid in kind of your antibody response as well. And this response is really what we're looking at, okay? So again, this is how these vaccines are working. And now that we understand that, now we can go over some of the interim and press release data.
Britain has a new weapon in its arsenal, one that it hopes will help control the mutant Wuhan virus. The AstraZeneca Oxford vaccine. British regulators have approved the homegrown jab. Millions of doses are all set to be shipped, but other countries do not seem to be in such a rush. India, for example, has sought more data from the makers of this vaccine. The United States is suspicious of the trial results. So why has Britain expedited the approval process? Our next report tells you.
It's been a strange holiday season for Britain. A Christmas under lockdown a rampaging Wuhan virus mutant, and some intermittent joy with the Brexit deal. Ahead of New Year's Eve, that streak continued.
This is really fantastic news this morning that the Oxford AstraZeneca vaccine has been authorised for use by the regulator. They've been looking very carefully at all of the information that's come out of the trials, and they've approved it for use, which means that we can accelerate the vaccine rollout.
Britain is the first country to approve AstraZeneca's vaccine. 100 million doses are being produced. Inoculation is set to begin on January 4th, but the US and the EU are not expected to follow. There is still some confusion about the perfect dosage. But with cases rising by the thousands, the Brits are willing to take a chance.
Yeah, I'll be taking it, and I think it should do, but I know there's a lot of people who won't be, and a lot of people I speak to don't seem to be interested.
The UK is vaccinating its people at record pace. The target is to cover 2 million people per week. AstraZeneca's approval is also good news for India. The jab is being manufactured by the Serum Institute based out of Pune. 50 million doses are ready to ship. All that's left is regulatory approval. An expert team of India's drug authority met on Wednesday, and indications are a green light is not far off. AstraZeneca promises to be a game changer. For starters, one dose is being sold for $4, much lower than the Pfizer jab at $20 and Moderna at $37. Storing it is also easier. The Pfizer and Moderna jabs have to be super cooled. They need temperatures of minus 70 degrees Celsius. For AstraZeneca, a normal refrigerator would do. But can it beat the mutant Wuhan virus? That's the big question, because the UK variant is spreading worldwide. The US confirmed its first case, a man in his 20s with no travel history to Britain. So did Chile, a woman who travelled to Britain earlier this month. In India, the mutant caseload has risen to more than 20. Contact tracing is key to controlling it, but not everyone is cooperating. Like this traveller who arrived in India on December 21st. At the Delhi airport, she tested positive for the Wuhan virus. Authorities asked her to quarantine for 7 days. But as soon as she got the outpatient card, she fled more than 1,000 kilometers away to a city in Andhra Pradesh. Thankfully, authorities had gotten wind of the plan. They were waiting for her at the railway station. Both the patient and her son are now in isolation wards. In the eagerness to put 2020 behind them, people are playing fast and loose with virus control measures. But the final hurdle is in sight. Now is not the time to let up.
Since the first humans harnessed fire, our big brains have been presenting us with challenges. Innovations that can bring us great good and also great harm. In the 15th century, the printing press allowed people to share knowledge, sparking the age of reason, and also upending the established order and authority of the church. Learning to master the winds and navigate the seas, humans conquered the globe and spread deadly microbes to populations with no resistance. In the 20th century, we split the atom, unleashing a power hitherto unimagined, and for the first time, introducing the possibility of our own annihilation. The speed with which our machines can learn has raised the prospect of the so-called singularity, the moment artificial intelligence vaults beyond us, creating a world in which we are no longer masters. And now, twin girls have been born in China who were genetically engineered with a powerful gene editing tool called CRISPR-Cas9. Their altered genes will be passed to their children and their children's children. We have discovered a tool that bypasses natural selection, giving us direct control over the levers of evolution. And again, we are challenged. This tool can bring us great good, more food, less disease, or great harm. Can we learn to use it wisely?